So as I was saying, we're going to look at numbers in nature that go up and come down and go up and come down and have a constant up-down ebb flow pattern. So that's how daylight hours work in the year. So in June, we have the longest day of the year, and then slowly the sunlight gets less and less and less and less until we hit December, where it's at the least amount of sunlight, and then slowly it gets more and more and more and more until we get back to June, where we have the most amount of sunlight, and then gets less and less and less and less, and more and more and more and more. So it's got a high peak and a low peak and everything in between it. So we're going to model this data for daylight hours in Lisbon for day one, and then you're going to model some other periodic functions for the next ones. So the idea of this is we're going to take all this data and we're going to put it to a sine function. Normally we're used to just seeing sine x, but now we're going to add numbers all around to add transformations onto just the basic sine function so it actually fits our data that we're looking for in real life. And we're going to use some technology to do this. So if you note here, there's a sheet for the spreadsheet of all the numbers from the front page. You're going to want to open that right here. Also note that on the bottom it says Lisbon and Stockholm. Lisbon is day one. Stockholm will be day two, so make sure you're on Lisbon. I just made a whole video, honestly, that used Stockholm's number, and I had to restart it because I wasn't on Lisbon. So make sure you're on the Lisbon tab for today. You're also going to want to open up Desmo.com calculator, and that's right here. You're going to want to make sure you're signed in with Google on the top right. We've done this before in class. You click the sign in, sign with Google. The reason why you got to do this is it saves your work in case you have to exit out of it. You can name this if you want. You can name this Lisbon numbers, whatever. I don't care. I don't need to see this. This is for your own good. So now what you're going to do is go to the Google Sheets and copy the numbers. So you're going to highlight all of the numbers in the Lisbon page. So from here down, notice how it turns blue when you highlight. Make sure you get all of them. I'm going to right click. I'm going to hit copy. I'm going to go to Desmos. You click right here. And then I'm going to click Control V to paste it. And what it does is it takes all my numbers, puts it in a table immediately, and it puts those dots as blue dots along here. Notice how they're just dots because I just gave points. I didn't give it a smooth equation like we're used to seeing in Desmos. All right, so this next step is really important. You're not going to see any difference if you do it, but you will later on. So you got to go to the monkey wrench right here and make sure that you are on degrees. Make sure it says degrees in green and not radians. This is going to be a huge difference in when we go try to plug in our final equation. So now our goal is to use that graph to find the values for A, B, C, and D and make them number values so then we could type equation here and it will follow the line. So the first thing we're going to find is A, and each one of these has its own little fancy trig vocabulary. So A is called amplitude, and amplitude is equal to half the different distance between the highest point and the lowest point of the curve. So we don't have data for every day of the year, but we do have a picture that kind of paints like we know that up here is the highest point, and we know down here is going to be the lowest point. So you can use your mouse to click on it, or you can use the table. So 13, 14, okay, 14 is pretty big, 14 is pretty big, and then it drops. So let's use, this is 14.9, 14.8. Ooh, this is 15.1, 15.1. Let's use 15.2. We're going to guess that the highest point is 15.2. Now let's look for the smallest number, which is like on the edges. So if we look in our table, we see a 9.1. We scroll down at the bottom, we see a 9. Let's say it's about 9. 9 is definitely one of the smallest numbers on this table. So now to find the amplitude, we are going to half the difference. So difference is subtraction. So 15.2 minus 9. And that's going to give us 9. 6.1. And then we have to take half that. So divide that by 2. We're going to guesstimate 3.1. Yeah, it's like 3 point decimal, blah, 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 blah. We just rounded it up to 3.1. So our amplitude is 3.1. Now we're going to leave it there. We're going to put it into that equation at the very end, so don't worry about it. Next, we're going to calculate B. Now, B is the effect on the period of the function. So I kept using that word period to say, oh, we want a periodic function, something that rotates with time, that goes up and down, and it goes back up and down again. So a periodic function follows something called a period. And B affects that period. So how long does it take for the function to repeat itself is the period. So if we increase B, the function shrinks. If we decrease B, the function stretches. The period of a classic sine function is 360. And the formula to find B is 360 divided by the period. So again, note we just brought up this idea of a period, but B is not the period. B is the period when 360 is divided by it. So in this case, we see the ebb and flow. So we really want to know what a full time around is. So this is its low point. It went to its high point, then it went back down to its low point. So if you had to guesstimate what it would do next is it would go back high. So to find a period, you look from low point to low point or high point to high point. Since we have low point to low point right here, we're going to just say, all right, it's to the point of here, which in our table, it says 354. And then we think about it. Wait a minute, we're talking about daylight in terms of the year. And we talked about daylight being this whole periodic thing every year. So each year it starts up different. How many days are in a year? Oh my goodness, 365 days. Notice how close that is to 360? So what we're gonna use is we're gonna use 360 as our number. So this function goes up and down every 360 days. So what is the period of daylight function? How long does it take? It takes 360 days about. And then it says calculate B. So remember on the other page, it said that 360 divided by the period is equal to B. Well, we just said the period is 360. So 360 divided by 360 is 1. So B is 1. So a yearly rotation of something actually follows the period of a sine function very well. Now we're going to calculate D. Yes, we skipped C, but we're going to do D first. The number D determines the vertical shift, so vertical is up and down, of which the position of daylight function along the y-axis with respect to the position of the function of the sine x. So all we have to do is decide which vertical direction and by how many units we need to shift up sine x to match the daylight function. So in order to find the vertical shift, we're going to take the highest point and subtract the amplitude. So we already decided what the highest point was earlier. So we said the highest point was 15.2. We're going to subtract the amplitude, which was 3.1, and we are going to get 12.1. So the vertical shift is 12.1. All that's saying is that if we move this 12.1 units down, that we have a normal sine function that works along here, but instead we took it and we put it up here. So our vertical shift is 12.1. Now we're going to calculate C. This is our phase shift. So if this went up and down, this changes it this way. So this determines the position of the daylight function along the x-axis with respect to the position of the function a sine bx plus d. So that's just fancy for saying, how did it shift this way? So the basic sine function usually starts with the value of d. So the value of d here is 12.1 at x equals 0. So we want to find the phase shift, then we just have to count how many x spaces away from 0 does it take to get to where y is d. So our y is 12, or our d is 12.1. So all we need to do is go to our graph, find 12.1 on the graph, which is about here, I think, almost. Oh, there's 12.2. So if this is 12.2, we want to know how, that's up 12.2. We want to know how far over. Oh, it's 82. So we wanted 12.1, so let's say about 80. So it went 80 positions here to find 12.1. So that means our phase shift is 80. Again, we're just finding where y equals 12.1 on the graph and then putting its x coordinate for our phase shift. So now all we need to do is replace all the values we found for this. So we found A to be 3.1. We're going to write the word sine. We found B to be 1. Remember, x needs to be there. It's a function. We found C to be 80. And we found D to be 12.1. Why did I write D? Who knows? Losing my mind here. So now what we're going to do is we're going to type this equation into Desmos on that second line. See how it says 2? We're going to type it right there. And see if that equation makes a line that follows these dots. So we want f of x equals 3.1 sine, and then I want to parentheses 1 parentheses x minus, that's my dog. He's a little angry. I don't know why. He doesn't like when the Amazon guy comes every day, and the Amazon guy comes a lot. He thinks they might come in and trespass, but little does he know we're in quarantine and no one can come in the house. 12.1. All right, so now that I typed that equation, notice how this is blue, but my dots are blue. Let's change that. What color do I want? Yeah, I'm not gonna be picky right now. So the dots and my equation match up perfectly. So what we just did was we modeled a actual table of data from real life with a trig function that we learned in class. This is the real use of learning how to graph things. Most of the time, you're not going to do what we did at the beginning of the year, where we are given actual functions and we have to learn how to graph them. We're going to be given data, and you're going to have to model it by filling in numbers into a function. So now that you have that equation, you can find daylight hours for any day in Lisbon by plugging them into X. So I want you to find the amount for January 30th. So January 30th would be 30 days. So remember, X was the number of days away from the beginning of the year. So you just put 30 into here, type in the calculator, make sure you're in degrees, and it'll tell you how much sunlight happened on January 30th. So you're going to do that on your own, and that concludes part 1 of this trig graphs in real life. Part 2, you're going to be doing Stockholm on your own, but you can use this video to walk you through how we did this day. Have fun.